micrófono.
Ya, perfecto. Perfecto. ¿Usted
Ya
me
estamos en vivo.
avisa? ¿Sí? ¿Estamos
Sí.
en vivo? ¿Nos estamos viendo? Ya,
Sí.
buenísimo. Tenemos gente, ahí se va a integrar más gente. Sí. El link se le envió a todas las personas, ¿cierto, Carlos? Me parece que sí, porque si no la gente no se estaría conectando.
Sí, profesor.
Sí. Katerina, would you like to wait for a little bit for people to enter, because there are a lot of people.
Whatever you
yeah,
guys need or want.
Maybe we would need to wait a little bit just to prevent from many people to enter
I am
at
flexible
once.
Until 6 p.m. your time and after.
Okay.
So
okay. Okay. Thank you very
don't
much.
worry.
Thank you very much.
Yeah, you do what is appropriate.
Carlos, ¿qué sugiere? ¿Que partamos al tiro?
Sí, podemos comenzar de inmediato.
Sí. Ya. Voy entonces a... Vamos a iniciar oficialmente la sesión. We're going to start officially, Kate. Okay?
Okay.
So, we're going to go the two languages.
Sí.
So, muy buenas tardes a todos. Muchas gracias por su asistencia. Falta mucha gente que se integre a la transmisión de hoy de la Universidad de Chile, en donde vamos a estar aprendiendo de la profesora Katerina Ziotopoulou de la Universidad de California en Davis. La profesora Ziotopoulou hoy día nos va a presentar su trabajo desarrollado en base al criterio de desempeño, problemas de liquefacción, y donde se van a mostrar tanto resultados numéricos como experimentales. Así que muchas gracias a todos por estar aquí presentes junto a la Universidad de Chile y su grupo de geotecnia. In English now. Thank you very much, everyone, for being here today at University of Chile virtually, right? We are here today to learn from a world-renowned expert, Professor Katerina Ziotopoulou. Thank you very much, Katerina, for being here with us today. Very good friend of our University of Chile. Professor Ziotopoulou will be talking today on the performance-based assessment of liquefaction-induced ground failure, element and system level considerations, which is a talk based on her research that uses a lot of numerical modeling and also experimental results. University of Chile, is the largest public university of Chile and is strongly committed to the development of its country. And we are very happy that you are all here sharing with us this moment to learn from Professor Ziotopoulou. Katerina, the stage is all yours. Muchas gracias for being here with us. And the rest of us will turn off our microphone and the cameras. Thank you very much again for being here with us, sharing your knowledge. Thank you.
De nada. So, buenas tardes a todos. I know this Spanish and I know a little bit more to thank you at the end. So thank you so much for inviting me here today. I was just discussing with Felipe about, despite all the things negative with the pandemic, I think, if anything, the access to knowledge and the access to people who are available to talk, but also from our perspective, the ability to meet all of you online, even online, I think it's something to keep in our minds. Of course, also, I would never take an online seminar in Chile above being actually in Chile and then seeing all of you in person. I have visited once in 2011, and I'm really looking forward to being back there. I have left a few locations unexplored, so I'm going to be patiently waiting for the pandemic to be over for all of us to meet in person again. So my scope for today is to talk to you about some of the recent work we have been doing at UC Davis And I have at the bottom of the slide and throughout the presentation, I will be telling you the context within which this work has been developed. And of course, you don't develop all these approaches and these findings on your own. It is virtually impossible. So progressively, I will be introducing you to some of my colleagues and students at UC Davis who have been valuable. So the title I have chosen is on the performance-based assessment of liquefaction-induced ground failure. And I want to touch on two aspects, one from the element level, but also then from the system level, so that we can all get on the same page about what it is that we are after broadly. So first and foremost, I want to start with defining the space we're working on and focusing on the performance-based assessment. The tool that we typically use are, numerically speaking, of course, nonlinear deformation analysis. And at the bottom of this slide, I have selected 3 examples of infrastructure systems that I will be referring to just a little bit later, just to start thinking about how wide the range of the problems we're dealing with is. And in each one of these systems, we may be interested in different aspects of their response. But broadly, when we refer to performance-based, we like to be able to estimate deformations, and nonlinear deformation analysis numerically are much better than simplified methods because they do account much better for the dynamics of the problem, but they can also accommodate more complicated geometries or conditions. Now, we need to be thinking that we may be doing nonlinear deformation analysis either to design new infrastructure or to evaluate existing infrastructure, and that gauges a little bit the types of things we may be after. Now, they are particularly valuable because they give us the ability to represent systems realistically, but they also give us the ability to investigate them extensively and perform parametric and sensitivity analysis so that we can identify the vulnerabilities of all the systems that we are after. Now, 2 things to keep in mind is that in any of these systems, the elements, the soil at the most fundamental level is represented by a constitutive model. The constitutive model connecting stresses with strains and giving us the response or the behavior of the soil overall. Now, of course, that constitutive model will be activated by the loading paths that are relevant in each one of these problems. And what I'm implying with that is that these loading paths are not going to be the same in all the problems that we're dealing with. So we're interested in different aspects of their response. At the same time, when we're looking at things from a system level perspective, the answer we get for a broader system is a synthesis of the tools that we use, that would be the platform, and the choices that we make on those, from boundary conditions to ground motions to interface elements to structural elements, every single choice that goes into there. The site investigation, and not the site investigation on its own, the broader understanding we have about the subsurface information, because that will help us inform the analysis we do. And then, of course, that connects to us having a broader understanding of the problem at hand. So one of the common advice that goes out is you shouldn't be doing a numerical analysis if you don't have an idea of what you expect and you go in blindly. Of course, putting such analysis together consists of many steps. Back in 2018, with Ross Boulanger, we published a paper in the Geotechnical Earthquake Engineering Conference in Austin. And we evaluated different aspects that affect the quality of the results of NDA studies. And the list of factors that may affect the outcome are listed here, and we can talk about the selection and the calibration of the constitutive model, so what happens at the element level, the limitations of the numerical modeling procedures we use, the quality of the site characterization work and how that connects to our understanding of the broader subsurface, the selection of the input ground motions, of course, the expertise of the analyst, but that goes together with having sufficient time and resources to really get the best out of everyone, let me put it like that. And then, of course, the quality of the documentation and review processes, because as you deliver something, it needs to be well documented such that people can review and give you feedback. And it's only feedback that usually drives developments as we move forward. In this presentation, I will touch on these two issues from two scales. The reason why I want to do this is because what we're dealing with here, and this is a nice schematic from the Oberkampf paper on validation and verification. And if we conceptualize the complexity of the systems we're dealing with versus the parameters that participate in their overall response, usually the tools that we validate are applicable for lower complexities and less system parameters. But as we move into application and practice and we deal with much more high consequence decisions, these two domains do not really overlap. And this is something common that we have in geotechnical engineering. So as we move from our knowledge to our application, to our predictions, to our designs, or to our reevaluations, we're making this leap of faith that we formally call inference. So when we want to increase the confidence with which we make this inference, in particular with NDAs, that will depend on the efforts we have done in the background to promote and advance best practices for this domain here, for the validation domain. And this has to do with mostly exercising ourselves and our tools against all the knowledge that we have from our data. So my goal for today is to share two cases with you, or to you, that show the relative importance of the various choices that we can make from an element level and a system level perspective, all keeping in mind that our goal is to enable reliably performance-based predictions. So first, I will talk about the element level calibration, a little bit about constitutive modeling, no equations today, not needed, and we will focus on the cyclic mobility regime, so post-triggering deformations for medium dense and dense sands. Then I will switch gears and I will move to a system level prediction that we have performed, where I'm going to draw some lessons about what was necessary there. So everything revolves around deformations and our ability to capture those in various contexts. So I'm going to move forward with the element level calibration. And since we're not meeting online, I think, or in person, I think it's always nice to put faces on the names of people that we talk about. This is some work that I did over the last few years with my friend and colleague Ziotopoulou out of Greece, Panchito Humire or Francisco Humire. He is from Chile. He will be graduating soon out of UC Davis. Amalia Giannakou, Jacob Chaco out of Greece, and Thalia Travasaru from Fugro here in California. So going a little bit into the motivation of this work that we did, and here I'm showing the various types of correlations, empirical or semi-empirical, supported, of course, from some theory that we typically look out for when we do liquefaction evaluations. And all these forms, and as I will touch on these just a little bit, those are the ones that provide a basis for developing engineering procedures, and then later for developing numerical tools, constitutive tools, and basically summarize all of our knowledge on what sands do in a liquefiable regime. So here we can see triggering, so basically cyclic strengths as a function of an SPT blow count. Sometimes you may see this x-axis as a relative density. We typically look at CSR, cyclic stress ratio, versus the number of cycles needed to cause liquefaction. So these curves capture the effects of load and duration, progressively increasing with the number of cycles. These curves here are different based on the relative density. So for higher densities, you will of course shift upwards and have higher strengths. These two relationships here, the K sigma and the K alpha factor, basically correcting our strengths for not being under 1 atmosphere, which is the reference overburden, and not being under level ground conditions, which is the static shear stress ratio of 0. So basically, as you increase your x-axis here, you're going to higher overburdens, and we're looking at how that would affect the cyclic resistances. Basically, you suppress the dilation of your material, that becomes more contractive, and thus materials will be weaker in terms of cyclic loading at higher overburdens. Here, as you increase the static shear stress ratio alpha, you're moving from 0 level ground conditions to sloping ground conditions. And here we can see that the relationships indicate that your material will be stronger if it's dense of critical, and it will be generally weaker if it's loose of critical, with some variations in between. For dynamic problems, we're definitely interested in the shear modulus reduction for increasing strains. These usually come hand in hand with damping and how that increases with shear strain amplitude. And of course, in the background, we always want to keep in mind the behavior of these materials under drained and undrained monotonic loading and their ability to honor peak strengths and residual strengths, the latency that connects the two, and of course, the agreement towards a common critical state as you shear them to high strains. For some applications, we may be interested in post-liquefaction volumetric strains. So basically tracking how the material will settle down as the pore water pressures are dissipating and the material is experiencing plastic volumetric strains. So all these relationships form a very nice basis, but looking into all of these, there's not much guidance in the types of deformations that sandy materials undergo. So looking at a typical response from direct simple shear testing on Ottawa F65 sands, these are all tests that Francisco has performed at UC Davis, and some others that I will be showing to you that we have summarized. So looking at a stress strain loop and a stress path, here I want to give some definitions. And here I will delineate between the gray region, which I'm going to call pre-triggering. We're doing triggering, at least for today, it's going to be a 3% single amplitude or a 6% double amplitude. And then we want to define this progressive accumulation of shear strains in the red regime here, the banana-shaped loops, as we like to call them, or the butterfly loops, as we like to call them, in a stress path, plot. So these are the indications that soil give us. Of course, this is an idealized loading condition in a stress-controlled DSS test in the lab with a progressive holding of them, or constant holding, I guess, of this amplitude. And of course, the way that this material will depend in the field will definitely depend on the boundary conditions that you have on it. However, the question now becomes, does this regime, does this red part of the response play a role in a system level analysis? And if it does, we currently have no calibration basis. We don't know how rapid this accumulation will be. And this can become particularly important if you are reevaluating existing infrastructure. For a new infrastructure, one might argue that you will not accept anything more than 3% and you will mitigate or you will prepare your site accordingly. But if you're evaluating some existing infrastructure, it may be important to know whether you're going to be at 4% or at 10%, because that may drive lots of the decisions that follow afterwards. So the data that we have do give some indications of progressive accumulations for the medium dense and dense sands. And the question that we came into this research that I will tell you about right now is, are there any patterns that are, of course, mechanistically sound that can help us develop, at least, if not a correlation, at least some guidance so that we have an idea about where we're going? So we started looking at tests like this one. And here now, this is the exact same test, but I want to focus on just one cycle in this cyclic mobility regime that we talked about. And the typical definitions that we give here is either the double amplitude of shear strain or a positive and negative single amplitude strain. So broadly tracking, how does this evolution take place? So we started tracking different types of accumulations for different types of tests. So here I'm showing you two tests. Each plot is one test. The green line is going to be the double amplitude, and then the red and the blue lines are going to be either negative or positive single amplitude strains. So we're basically seeing how the strains open up, how the strains evolve throughout loading. And of course, we can see that initially, as you increase the cycles, which are on the x-axis, the shear strain essentially is 0. And then, of course, after a little bit, it starts picking up. We define post-triggering the threshold wherein the strains overcome 3% single amplitude or 6% double amplitude. And we like to observe how this evolution takes place after you have triggered in the cyclic mobility regime. So we started collecting data. Now, sneak peek, we are doing some extensive tests to see what we can gain out of these relationships. But we started observing that generally, this seems to be a more or less constant evolution. So we started tracking the slope of this, which is essentially a shear strain increment per cycle, if you want to put a number on each one of these slopes. So the approach we developed was to start looking at different types of data under various cyclic shear stresses, or different relative densities, or overburdens. And basically what we track is this increment, the progressive increase of shear strain per cycle. Now, in these plots that I'm showing to you, the darker line is a looser specimen for 42%. I mean, it's pretty much obvious because it does accumulate strains faster, so it's weaker. And then the lighter green, it's a higher density compared to this one, but again, a medium dense one. So if you track the slopes of what I showed you before and you fit them, and we fit them with a line because we had a lot of indications that it was a line. So we track only now shear strains in the post-liquefaction regime. So you need to start thinking about what that would mean now for a system level perspective versus, of course, the number of cycles after the triggering of liquefaction. So we're only focusing on the cyclic mobility regime. So broadly speaking, and for these two tests only here, we can see that the progressive accumulation is much more rapid for the looser material and much more slow for the denser material. And that made sense. So we started looking at more and more data, and there's plenty of data out there thanks to researchers who do share their data. In our paper, we do list all the resources. But the bottom line for us was that we started tracking this delta gamma, so the slope, basically any slope on these charts here, delta gamma per cycle, versus all the relative densities that we had available from the data we found in the literature at the time. So initially, as you see this in this semi-log space, there seems to be a trend, which was enough of an indication for us to keep exploring. So one data point here, imagine, is just one test and the slope extracted from it. So we started looking at more tests and more conditions. So here I am showing stress strain and stress paths. And then at the bottom, I'm showing you these slopes that we're tracking. Now, in this case, we have two identical cyclic stress ratios, but those are under two different overburden stresses. So the blue test is under 100 kPa, and then the pink-ish purple test is under 200 kPa. What this implies is that the cyclic amplitude, that shear stress amplitude that is getting applied, is definitely higher for the higher overburden, such that this CSR is staying constant at 0.3. So evidently here we see that the accumulation of strains is also different, and it's shown here. The denser, sorry, not the, so they both are in the same relative density. The material under the higher overburden suffers a stronger, a faster accumulation of strains, while the other one doesn't. And as we were trying to summarize these, and we started to see like what makes sense more mechanistically, and these are data, for example, from Fraser River sand, we started looking at whether ways to normalize this to see if they can come to an agreement. And of course, we know from the critical state framework and the fundamental understanding of sands that essentially some things need to be normalized. So the latest thing we saw was that if we normalize the shear strain accumulation post-triggering with the amplitude, not the CSR, the amplitude, the absolute amplitude of the cyclic shear stress, more or less all of these agree to a common percentage per kPa. This is just unit consistency here. So when we started looking at these normalizations and coming back to the framework that I showed you before, we saw that the moment we did this normalization, and you can think about it as an inverse stiffness, because this is what it really is. Stiffness is usually shear stress over deformation. Here we're looking at deformation over shear stress, essentially, and we started seeing even stronger trends and correlations. So this was just for Fraser River sand. So we kept collecting data, and progressively by looking, and these are all experimental sands, so just like idealized, uniform, clean sands in the lab, we started seeing that there is a very strong trend that each sand follows, but overall, all the sands do follow something that can be called as consistent, definitely. So we call this rate the compliance rate, and then we defined this semi-empirical framework because it does have some fundamental mechanics in there, but also it is a synthesis of observations. We define this compliance rate, basically this inverse of stiffness, capturing how likely is a material to accumulate strains as you keep shearing it. Later on, and I'm not going to show it, we saw that there's a dependency here on this relationship, and this B value that I have kept as just parametric B, there was a dependency on the D50, the median grain size of the mean grain size, sorry, of each sand. Now, of course, to maintain some perspective here, these are only clean sands. All have been prepared with dry fluviation, so we don't have much of the effect of fabric here. And all of them were close to 100 kPa for their overburden stresses. So we have very few at higher overburden stresses. All of them were direct simple shear tests, apart from the inverse orange triangle ones on Toyota sand, which were hollow cylinder tests. Okay, so we arrived at this framework, or at least at this indication of that there is a relationship. And then we said, we have to see what it means from a system level perspective. Can this provide a good enough guidance to capture a system level analysis better? So we picked a problem that has been quite well studied, both from numerically and with centrifuge model tests, and that was the Transbay Tube. So here I'm showing you a schematic, the simplified schematic of the configuration of the problem, and then an idealized flak cross-section analysis. So the offshore Transbay Tube, this now we're talking about a 5.8 kilometer long immersed railway tunnel that is in San Francisco. So basically connects Embarcadero approximately with Oakland, that is right across. Fugro assess the vulnerability of this Transbay Tube, TBT for short, to uplift resulting from liquefaction from the surrounding soils. So here, what you see here, this fill here and underneath, they were considered to be, as you see here from the values, are quite loose, best case scenario, medium dense. So there was a concern that if these were to liquefy, there would be a significant uplift of the tunnel through its soils, and then basically with very increased consequences. I don't even have to describe those. So to assist in this direction and to facilitate these predictions, back in 2007, there were two centrifuge tests that took place at UC Davis at the large-scale centrifuge facility. The input motion used was the Chi-Chi motion from the 1999 Taiwan earthquake with a PGA of 0.65 Gs. Now, the centrifuge model of this Transbay Tube included the submerged tube, so you can see it here or here. It was surrounded by a liquefiable fill. This is the yellow one, and the foundation course. The green one here, that's basically like loose gravel under the tube. The Monterey sand was used to represent the loose gravel, the green one here, and of course, the fill here around it. Now, interpreted CPT data that we pushed, that's the editorial CPTs were pushed to give a sense of the relative densities and how those were achieved. And the as-built relative densities, I'm listing them here for the Nevada sand, that was the cover. Here were 32%, 50% for the Monterey sand here, and 40% for the Monterey sand, representing the loose gravel as a foundation course. This was all built in a rigid box with windows on the side to track different movements and see what actually happens. Now, Here, I'm going to show you now an actual cross-section after the test. These are some colored vertical lines to track the displacement, but this is also a sneak peek into the strain contours that we observed after the analysis, and of course, 3 points that we track. So what is particularly interesting here is what is the mechanism controlling this uplift? And turns out that the primary source of uplift is due to the shearing of the liquefiable backfill soil. So you have basically movement of the surrounding soil towards and underneath the tube, and this results to a sideways movement or ratcheting, if you'd like, and then a progressive ratcheting also upwards and uplift push of this tunnel through the heavier and softened liquefiable soil. Okay, so here we see the experimental observations, we see some of the numerical analysis, and we see that the deformation patterns do agree first and foremost. The question is, how can we be accurate enough in the prediction of displacements and the level at which they are controlled? Now, back in the day when the first simulations took place, it was shown that the uplift is not going to be as excessive as people were afraid, and Caltrans and the BART tube overall, they saved a lot of money in just deciding to do a mitigation rather than a more destructive, I guess, approach towards fixing this. But now for us, this has a lot of research interest because we can investigate and validate our analysis and the calibration of our tools against these very well instrumented centrifuge model tests. So I will show you the analysis we did more recently after, of course, having in our hands this framework that I showed you before. So looking at these materials and then looking where the deformations are controlled, we selected to apply the consecutive model PM4 sand for liquefiable materials, and that was assigned to the medium dense Monterey sand, the one that was the yellow and the green layers that we saw before, but also the looser Nevada sand that was the sand fill, the purple sand fill that we saw around it. Now, of course, we did some calibrations on both, but in this time around, we emphasized both the triggering of liquefaction, but also the post-triggering strain accumulation, understanding and thinking that this progressive ratcheting will be controlled at an element level from this cyclic mobility regimes. So at the top part of this plot, I'm showing you the calibrations and the data for the Nevada sandfill and the Monterey sandfill. What you see as data points, these are experimental information, and then the continuous lines are the calibration of the model and the different targets that we were looking at depending on which material we're looking for. And then for the Monterey sandfill, about the same story with data points being from actual lab tests, and then the calibrations trying to capture those. And we can see that this was pretty straightforward with activating few of the parameters of the model. And I'm going to talk about those just a little later. The additional step, though, we took is that we isolated from our framework both the median prediction, but the ones also for the Monterey and the Nevada sand. And we did some calibrations targeting at approximately capturing that as well, keeping in mind that we didn't have any other guidance to go by. So if we now go and see what happens from a system level perspective, here I'm showing you results in terms of the deformation, the uplift in centimeters, the pore pressure evolution at point P5, that was the point immediately underneath the tunnel. And at the bottom, I'm showing you the acceleration time history. So this displacement is tracked right at the top of the tube with the instrument DVDT1. Now, a few things we see here is definitely we can see it from the pore pressure time history. We can see it from the uplift. Liquefaction occurs at about 12 seconds. And this is, we can see that in both. And this is something good, but also intentional because that's how we calibrated our triggering. And it turns out that it showed also from a system level perspective. At the same time, together with triggering, we have this commencing of this upward movement of the tunnel that does develop under the post-liquefaction regime. Now, the experiments are the blue curve, of course, and then the red one is the numerical simulation. And I don't have the results from the previous investigation, but I can tell you that these ones, I don't think we can do any better than this one based on our current capabilities. And this is pretty satisfactory. Turns out that this accuracy, and as we investigated through some parametric investigations, is affected by the appropriate calibration of the constitutive model and the emphasis not only on the triggering, but also in the post-triggering or post-liquefaction, if you'd like, shear accumulation. So this is a problem where this ended up being particularly important. In our paper, we feature one more example, and that is a centrifuge test that has a retaining wall. And that is also a problem where the lateral deformations of the retaining wall are controlled by the cyclic mobility lateral strain accumulation of the backfill. But I'm not having them here, just being aware a little bit of our time. Now, some remarks for this part one at the element level. We noticed a certain lack of guidance on how to account for strain accumulation in the post-triggering cyclic mobility regime. Of course, this is not hinting, that our community is behind. It's definitely hinting at the fact that it's not a problem that is always important. I chose to show you a scenario where this ended up being important, but sneak peek, I'm going to show you an example where this did not end up being so important. But regardless, we wanted to investigate what is happening there. Can we do anything better, assuming that you want to, for example, evaluate an existing infrastructure system? So the semi-empirical framework we worked on was developed on the basis of undrained DSS tests on clean sands from the literature, and it did demonstrate a relationship between the rate of strain accumulation and relative density. When we did our two validation studies, I showed you only one. We saw in both a very significant improvement in our ability to predict system level displacements that was not otherwise feasible before, without emphasizing the post-triggering cyclic mobility. Of course, we have to recognize that the database we worked with at the time was not exhaustive, but it did give us a hint about relationships between intrinsic properties and engineering behavior. The intrinsic properties being the D50, I told you about that. But I think there's much more things to explore. And it's not like we did not know that all these things are connected at the grain level, but it's one thing to suspect something or to see different efforts to establish it, and it's different to see what it would mean from the perspectives of constitutive model development, calibration, and then a system level analysis. Our current work of Francisco Humire and Rachel Reardon at UC Davis is currently exhaustively investigating experiments on all other aspects. So now we're looking at more sands of various gradations and other grain sizes. And we keep revisiting this framework at different overburdens, at other relative densities, to keep exercising and see what is happening there, but also understand what is happening in the background. What are the mechanics behind these behaviors that we observe? Our long-term goal is to develop more comprehensive frameworks that more exhaustively track intrinsic properties towards, of course, reliably predicting system-level performance, both in triggering and in deformations. Now, of course, the other long-term goal is to keep investigating other system-level scenarios and the applicability or even the importance of going there. So this is now going to connect me with the second part of this presentation, and I'm going to talk about ground deformation. So now moving to the system level from the Balboa Boulevard case history. And this is work that has been led by my student, Renmin Pretel, over the last 3 years or so. It was part of his master thesis, but we keep revisiting and refining mainly because we find it very interesting, but also Dr. Craig Davis, who was instrumental in giving us access to some of the data and, of course, his memory from this historical failure. So switching gears a little bit and now seeing some actual pictures instead of only idealized diagrams. The 1994 Northridge earthquake happened on the 17th of January of 1994. It was a moment magnitude of 6.7. So here I'm showing you an overview of Southern California. Los Angeles is here, and I'm going to zoom in here, and I'm going to focus on this built area here, which is the San Fernando Valley. For those of you familiar with more case histories, I'm going to zoom in furthermore. This pond here, this is the Van Norman complex, where the San Fernando Dam failure had happened earlier in 1971. And the juvenile hall slide, which was studied by Les Chiaud and John Stewart later between 1971 and 1994. So it's a pretty busy area that has given a lot of data throughout various earthquakes. But what the case study that we wanted to undertake is that of the Balboa Boulevard Avenue. So we're talking about a north-south oriented street, quite a wide street, not quite an alley. So we're going to see the types of deformations that took place here. Now, to keep some perspective, we have the mountains here. So the environment here, the positional geology environment here, basically is mostly alluvial deposits, and we're going to see more about that later. One more extra thing, that the closest recording station here was the Rinaldi Receiving Station, RRS, for short, which recorded a peak ground acceleration of 0.84, and that's the closest available for this particular study. Seeing now what actually happened there, those of you closer to the earthquake field will have seen some version of this picture, which basically showed both water pipelines and gas pipelines erupting, the gas pipelines getting ignited and having these very impressive pictures of water coexisting with fire. And then, of course, these massive craters that I'm showing here. So we basically had two water trunk lines failing with different diameters, but that doesn't really matter for what I'm going to talk about today. We had one gas transmission pipeline failing that was half a meter in diameter approximately, and at certain locations, and I'm going to show you where the pipelines experienced some compressive shortening of about 25 centimeters. So now, the fact that these broke is not a mystery, seeing what happened actually to the soil. So the real question becomes, why did the soil fail so much, to speak very colloquially, and why did we not expect it? Okay, so that's the particular interest here. So now I'm going to show you a plan view of the street that we're interested in. This is Balboa Boulevard. North is going to be facing to the left. And I have some of the surrounding streets. Approximately the slope of the street is 2.6% southwards. So this is a plan view of the types of cracks, deformations, and bigger craters that opened up. So the red lines are ground cracks, but most importantly, we're interested in these thick gray zones, a zone of extension to the north and a zone of compression to the south. It's easier, of course, in the field to measure the opening of an extension zone. It's going to open, you can measure it, but for the zones where you have compression and they just, you know, do a deformation pattern like this one, it's a little harder. But for now, we'll just consider that the average measured horizontal displacement was between 45 and 55 centimeters, supported from ground measurements and some aerial measurements performed right after the earthquake. The pipelines that broke were running approximately underneath the middle of the street, and I have these here with a blue line. So after the earthquake, various researchers investigated what may have happened. And those of you who have studied either more simplified liquefaction approaches or some of these case histories will have seen any of these hypotheses here. Some have suggested liquefaction and cyclic softening of lean clays. We're going to see the subsurface conditions in a bit. And then other researchers have suspected either a seismic compaction of unsaturated superficial sediment, so more close to the surface, or the co-seismic displacement caused by secondary faulting. When we touched this case history, our goal was to, of course, re-examine it and see how well we can do with the more advanced tools that we have in hand, investigate what may have happened, and then, of course, see how close we can get to these observations given the tools that we had available. So I'm going to talk first about the site characterization and the data we have available. And before I do that, I'm just going to say that this is a very well characterized case history, which is why it makes it so particularly appealing. It can help us learn a lot from the field. So in terms of data, back from April of 1995, we had basically available 17 CPTs here, right here on this west alley, about 50 meters approximately away from the axis of the street. And then on the east alley, also some CPT measurements from SoCal Gas. So out of the 17 CPTs, the 13 were paired with borings, and samples had been collected using Shelby tubes, and of course some SPT blow count measurements. There were also some field vein tests performed that help us constrain a little bit of the undrained strength of our more clay materials. Together with that, there were some monitoring wells that were installed to track the water table. So these are the locations where we have all the underground information, both from USGS and from from SoCal Gas. So we're going to project all of these right here. The reasoning behind that is that they're close enough to each other, but they're also part of a common depositional environment, and we don't expect much of variability on the east-west direction. We expect all the variability to take place on the north-south direction. So we felt comfortable doing that. So focusing now on this cross section, I'm going to show it now in this slide. And first and foremost, I want to focus on the 4 units that are present at the site: Unit A, B, C, and D. As you can see, Unit C is the most, that's quite variable, and I will talk about it in a bit, alluvial deposit. The top layers are more fill and some sands. Now, the water table has this shape here that is admittedly quite odd. I'm going to come back to this in a bit. And the one thing I want to focus on for now is the location of the maximum extension. So that big crack we saw before, that gray zone in our plan view, is approximately extending in this location. And then the zone of maximum compression is about here. Now, I talked a little bit about the water table, and the water table does admittedly look like that. We talked with Tom Holter after the much more recently. There were all these piezometers and monitoring wells that tracked what happens to the water table, and that was for 18 consecutive months following the earthquake, just to see if this happens to be some seasonal variation or something else that makes it look like that. But all the field observations, from the color and the saturation of materials to the numbers that the piezometers were giving, and the existence of a suspected fault right here, which we have now with question marks, everything points to the direction that this is exactly how the water table looked like. So we performed our analysis accepting this reality. I want to zoom in on one of these so that you see exactly what we're dealing with. And here we have categorized basically the soils based on the estimated soil behavior type category. So sand-like, if you have an ISFC index less than 2.6, or a clay-like if you have one that is above 2.9, and then we consider transitional soils or intermediate soils for anywhere in between. We did this categorization by tracking in this soil behavior type chart from the CPT data and basically seeing where each one of our samples, because if you remember, we did have samples where each one of these plot here. Now, from this, and based on what we saw, it seems that a 2.9 boundary between sand and clay-like is much more appropriate for this case. What this index does is that it really shifts the boundary between how much sand and how much clay we have in this cross section. So what we're dealing with here is that if we have 2.6 as a boundary, then that means we have more than 20% sand. And if we go all the way to 2.9, we have more than 55% sand. And this is something that we saw as an indication. We still considered those two boundaries, and then we evaluated what happens for various considerations in between. So let me return now to the cross section and see what we can obtain here. And this is a step that it's usually good to undertake. Just take a step back and see, what do you think happened in this case? So there's a few things that I want to point out here. I want to point out, first of all, that the zone of maximum extension and the zone of maximum compression more or less agree with the locations wherein the water table is saturating unit C, and then again, it goes down deeper. So here it starts saturating, stays up, and then it dives down. And this is exactly where the compression happened. Now, what happens if your water table is higher up in this alluvial deposit? Well, what happens here is that you saturate these sands, and you can see here you have a strong appearance of sand. Likely, if this is loose enough, it will liquefy or at least deform significantly. And here you have some clays that seem to be really, really weak. So the suspected failure mechanism that we have here is that of a larger mobilized sliding surface that, of course, led to the pipelines to extend extensively here and then compress extensively to the south. Moving forward with selecting some properties and evaluating what kind of strengths we had there at the area. This is just an indicative QTN depth distribution, not just one CPT location, where we just separate now sands from clays based on a 2.6 boundary between the two. Now, if we transform this QTN to a QT1 NCS, normalized cone penetration resistance for clean sand, corrected, of course, we want to focus on how would we obtain a property for unit C, because it seems that unit C is going to be the most responsible one, if you'd like. So we track cumulative distributions of these strengths just to see where the median would be. And just from one distribution, these yellow points here, we see that the median is about at 95, at a value of 95 for the 50th percentile. We, of course, perform a similar assessment for all the locations of CPTs and tracking all the strengths that we see here from the unit C. And we then track all the cumulative distributions and then the median one, which points at a value of 90, corresponding to a relative density if you follow the relationships with the CDQ parameter. Here in the CDQ parameter, for those of you familiar with this transformations, was 0.9. So keeping in mind now, everything we do carries some uncertainty here. We do see a relatively narrow band for this distribution, but on top of that, consider that we do have an uncertainty on the CDQ parameters as well. So here we're looking at a minimum of 60 and a maximum of 140 for this median value. Looking now at the clay-like portions and focusing on how we would obtain an undrained shear strength. This one now, the SU was obtained from tip resistances following the correlation where with the NKT value. The NKT value was constrained from the field vein tests so that we can have an agreement between both. And the value we ended up working with was an NKT of 16.5. Now, performing a similar type of evaluation and tracking where our SUs are and compiling the data across the whole site. Ultimately, we want to honor this variability, and we will be honoring that variability, but it is impossible to assign one different value at every possible zone where we had a CPT. So seeing now the distributions on the SU for all the CPTs across the site, we can now even visually see that the uncertainty is much, much larger, with SU values ranging, median SU values ranging from 34 all the way to 210. And the median is at about 80 kPa, but with a much, much wider uncertainty. So the strengths here are pretty variable as inferred by the cone, but what we get from this is that there's definitely some pockets where the strengths are lower, and this is something to examine later. Okay, now let's go and see now what this all means for nonlinear deformation analysis, thinking again and again that we are after displacements in this case. So our numerical model extended to the left and the right of our bounded, I guess, CPT measurements. We cannot go outside of that. We have no basis to assign anything, really. So we're talking about a model that is approximately 570 meters long. Units A and B, as I said before, are all going to be sand-like soils. Unit C are going to be these interbedded sand-like and clay-like soils. So we're going to try and honor that. It seems and it proves to be really important. And then Unit D is more of a stronger layer that will essentially be an elastic base. So this is an exaggerated, so it's a little more tilted than it should, just so that it can fit the slide. This is our model, 566 meters to be exact, with an overall 2.6% gradient slope. We perform nonlinear deformation analysis. Here I'm giving you some of the numbers or on the elements. Of course, all of our emphasis was on this interlayered deposit. Now, in order to bring this to reality, or at least to our simulations, we perform these stratigraphic realizations through the use of the CPT data, conditioned having, of course, our realization, conditioned on the CPT data, given a specific I sub C cutoff. So if we slide that scale to the left and the right from 2.6 to 2.9, you will see a stronger participation of sands and a progressively less participation of clays, depending on where we put that cutoff. So we did that through the TPROGS software, which basically evaluates the likelihood of transitioning from the one zone to the other, and accordingly assigns these pockets here. In terms of motions, I'm showing you here the models, but I'm going to show those a little later too. We applied the horizontal component of the Rinaldi receiving station. We did some investigations about that motion there. It was applied as a shear on this inclined base. And of course, assuming that this inclination is mild and it won't affect the ground motion much. So the vertical component from the RRS station was applied as recorded without any modifications. And that increased, as a sneak peek, the horizontal displacements by 5 or 8% alone. So it wasn't found to be very influential. Now, for our soils, I'm showing you here now just so that you see, and without making green be the good guy and red be the bad guy. In all the sand-like appearances, we applied PM4 sand. I'm going to show you some of its parameters in a bit. And then in all the red or clay-like soils, whenever they were appearing, we applied the PM4 silt model. And this is where the majority of our effort went, understanding that this was the critical layer. So PM4 sand, I hinted at a little bit. that was actually the topic of my PhD from 2010 to 2014. We keep developing it, we keep evaluating it. Everything is available on this website that I'm showing to you here. But most and foremost, I want to focus on the 3 primary parameters that it needs in order to be able to run. Now, the relative density from CPT or SPT data, the shear modulus coefficient calibrated against in situ shear wave velocity measurements, so basically constraining the low strain responses. And one of the primary parameters that does need calibration, that is the HP0, the contraction rate parameter that basically controls how fast you're going to go to your triggering criterion. For us, triggering here again and again is 3% at 15 cycles. In the background, there are 21 secondary parameters, and what those parameters do is that they ensure that you honor all that very busy slide with all the relationships that I showed you before. Of course, depending on the available data that one has, those can get activated, okay? They're not fixed, they just have some default suggested values. At the bottom, I'm showing an illustrative response of a stress strain loop and a stress path. For our Balboa site, these are the key data we were dealing with. I told you how we obtained this 90 value for the QT1 NCS. The shear wave velocities gave us approximately 240 meters per second. And then the cyclic resistance ratio based on commonly accepted relationships was fixed to 0.12. This led to the information of the 3 primary parameters, and I want you to hold this number here, this 50%, because I'm going to vary that a little bit later, recognizing that there's the CDQ uncertainty there, and that narrow but still some band in the uncertainty of these sand strengths across the site. The G0 and the HP0, G0 was determined based on shear wave velocity. And HP0 was progressively, iteratively changed so that we can honor liquefaction triggering at 3% with 15 cycles under the cyclic resistance of 0.12. Okay, so for the PM4 silt, similar philosophy, but just a model that was developed for clay-like soils. Low plasticity silts and clays actually can get used for higher plasticity clays, but that's a topic for another time. Similar philosophy, similar framework, but cast in a way that it can capture the responses and our understanding of how clays and silts perform in the field. So we don't have a relative density anymore as a primary parameter. We have an undrained strength at critical state corrected for earthquake loading rates, understanding, of course, that the rates at which you are imposing in demand in your field is very different from the rates at which you're exercising a material in the lab. So we have to be aware of that. And the other 2 follow exactly similar philosophy to PM4 sand. An illustrative response here, emphasizing a little bit the honoring of different shapes and areas in the hysteretic loops for clays or silts. And then, of course, a progressive shedding of effective stresses in a stress path regime, but not quite making it to the origin, leading to 100% excess pore pressure. This is quite typical for silts and clays, and actually this is one of the parameters that is there is a parameter that controls this in the background. If somebody has site-specific data, then this can get totally calibrated. Similar to before, these are inputs. I showed you before how we obtained this 80 kPa median value for the undrained strength, and then the shear wave velocity and the B exponent basically controlling the relationship between cyclic resistance and number of cycles. So this was directly assigned to the model, and the other 2 were either calculated for the shear wave velocity or calibrated for the suspected cyclic strength. I'm going to go to results, and I'm not going to go extensively over results. I'm going to go over the ones that help us learn something about our ability to predict lateral displacements in this case. So here I'm showing you just for a baseline analysis with all median properties, the shear strains really, really large across the site. Of course, in FLAC, we cannot get any localizations and any cracking opening up. So we have to infer what actually happened in the field. And that's quite straightforward, especially for scenarios like this one, having shear strains up to 30% occasionally here. The maximum excess pore pressure ratio, you can see that it easily made it to 100% for the locations where there was sand, and then it remains somewhere below that, around 70% for all the locations that had a clay assigned to it. If we see what we do in terms of displacements, I'm giving you a reminder of the plan view here and what we're really after. Here, I am tracking horizontal displacements. This is a contour side plot for what happens here. Of course, you can see that the maximum displacement is experienced somewhere here in the middle. But if you closely look at this, then you can see that the displacements do imply that there was a larger mobilized displacements from the beginning to the bottom. So we could look at this a little bit more broadly and think about what that means for our site. So in the remainder of the data that I'm going to show you, I'm going to focus on the maximum displacement measured here. In this case, for example, we would be looking at this location here, but I want to use it more as an indication of how well are we doing on average, okay? And in cases like these ones, you have to start from the average first before looking deeper into other effects. So first, I'm going to show you maximum horizontal displacements. This is what we're looking for on the vertical axis. Remember, we had approximately 45 to 50 centimeters, 55 centimeters. On the horizontal axis, we have some of the ground motion realizations that I went over in passing before. I did not tell you any of the details, but really they don't matter much. The colors here show the I sub C cutoff. So if you have a lower one, that means that for anything below that, you have sand. And then as you go to higher ones, you have more sands and less clays. So here, of course, the curiosity is, didn't you do a uniform model? Yes, we did a uniform model, and it either over predicted, if you consider everything is a sand, or it completely under predicted if you consider that everything is a clay. So we wanted to do just a bounding sanity check about where we are with displacements. Now, these are peak deformations or displacements right around the site. And these later we kept enriching with doing some sensitivity analysis. So here, these data become more because I want to show you what everything that we examine. So we examined different stratigraphic realizations. Here I am showing 4, but I think Renmin did 20 or more. I don't know anymore. If he's online, then we can call him out. And then we examine a range of I sub C cutoff values. So one thing to note here is as you move to a higher I sub C value, then you have a more predominant appearance of the sand in the site. And that, of course, collects the displacements in a more narrow band, as you see here, from yellow to pink to blue to brown here in each scenario. And here, of course, we have variations of 2 things. We have the variations of the undrained strength of the clays. We saw that that was just a median, but you remember the bound was much more wide than that 80 kPa value we assigned. And we also varied the relative density. And I don't want to go over the details of this. These are all, Renmin has documented these amazingly in our papers. I just want to bring out the point that, yes, there is a scatter, but around the scatter, we can say very comfortably that our average prediction, with all the uncertainties and all the decisions and all the selections that we made, we do go around a 50 centimeter median. Okay, so this is one important thing to keep in mind. Now, of course, the question is, would post-triggering calibrations matter? And what was the actual failure mechanism that happened? So the benefit of doing NDAs like these ones is that you can actually interrogate your model much deeper than you can when you're running more simplified methods, and you can really extract much more valuable information from elements. So this is what we did. So talking about this suspected mechanism and looking it in cooperation or coordination with a ground motion, I'm showing now our grid on the left just so that you know where approximately we're looking at. And now I will be extracting element level information about what had possibly happened for one realization with a reasonably selected I sub C cutoff. So the Rinaldi receiving station is famous because it was recorded during the 1994 Northridge earthquake, but it's also one of the motions that has a very strong directivity pulse featured in it, which we have here with blue. So the question is, how do the deformations progressively take place? So first, I'm going to show you the sand element here. Where is it? Here. This green element here, which is at that weak pocket that I told you before, approximately, if you remember, in the middle of the cross section. And we track stress strain loops, of course. The only difference between the two is that this one is a zoomed version for the beginning of the pulse, and this one is more of a zoomed out version of the whole stress strain history. So we see that during the pre-pulse regime, we have very little deformations taking place. And what really happens is that once this pulse comes in, the sand and pretty much all the pocket around it quickly liquefies, goes to 3% within just that quarter of a cycle or half a cycle, if you want, okay? And then from there and on, it remains highly deformed, but then it ratchets around it. The other thing to observe here is that because it is so soft, these materials progressively lose their strength. So you don't have even much of this cyclic mobility that we talked about before. At the same time, if we look at the clay-like zones, whether you want to look at this one or this one, we observe something really interesting. So the clay-like zone one, the one that is immediately north of the liquefied sand-like zone, does progressively accumulate, and quite rapidly, I would say, not progressively, rapidly, a high shear strain that takes it about to 3%. And then, of course, it experiences, you know, these stress strain loops with some hysteresis. And then later, as you enter the regime after the strong part of the motion, it's just cyclic deforms here or stays put. What happens here, though, at the clay-like zone immediately south of the sand? What happens here is that really, once the sand triggers and once we enter this pulse part of the motion, it accumulates very rapid and very strong compared to what happens later. So it does this half cycle, very large shearing, makes it all the way to 3.5%, and then it stays put there. Now, what we were able to describe from this one and conversations with Craig, who has been working in that area, he was the resilience manager at the Los Angeles Department of Water and Power, is that what pretty much happened here is that you had a very localized liquefaction of the sand pocket that collaborated basically with highly softened clays around it and led to that failure that ended up, of course, then progressively and retrogressively on both directions, affecting this much bigger area. And of course, for the people who know the site, this is why some researchers have been reluctant to describe this as a liquefaction case history, because if you remember from the realizations I showed you before, there wasn't so much sand in the area. Of course, there was a lot of sand, but not so much to unanimously call it liquefaction. So it was a little bit of both, and definitely a lot of collaboration, but for a bad cause. So thinking about this, and I don't have them here because I don't want to take up any more of your time. In this and thinking about the site and the materials and the mechanism, this is one of the scenarios where calibrating for the post-triggering cyclic mobility would not really matter much. okay, mainly because this problem is not like BART and it's not like the retaining wall we run, but it's governed by deformations and problems at a more larger system perspective. In fact, we did some extra parametric investigations and we said, okay, let's entertain the idea that cyclic mobility might have mattered. Turns out it doesn't. The deformations do stay high as in our baseline scenarios, and they only kick in just a little bit once you have a realization that has many more sands than clays. Okay, so this goes together hand in hand with that. So to wrap up the second part of my presentation and then my presentation overall, we performed 2D nonlinear deformation analysis with both constitutive models, PM for sand and PM for silt. We did stochastic realizations because we wanted to honor this spatially variable alluvial deposit, which was the guilty, I guess, in that scenario. We obtained a quite variable range of displacements from 30 to 70 millimeters, but definitely the median of those was 50. Sorry, this is centimeters. I have a typo here. So that was too low. 50 centimeters. That indicates that given all the uncertainties, as I said before, and all the combination of tools and procedures and data that we have, it still does pretty well. Our indications are that this case history and this failure was a little bit of both liquefaction and cyclic softening for this ground deformation here. And what we observe is that for this scenario, the post-trigger and trigger accumulation does not affect the answer much. This is a very useful and interesting outcome. Admittedly, at the same time, it is really hard to pick up the complexity of the site and the role of these different materials without looking at some greater detail, both from the stochastic realizations, but also from the NDA study. As final remarks, I want to reemphasize the importance of nonlinear deformation analysis to evaluating the seismic performance of geotechnical structures. And in this way, they are very valuable and much more an improved basis for estimating deformations, especially in the context of performance-based evaluation. Now, more broadly, and the focus of this presentation today was that when you're doing nonlinear deformation analysis, you have to be looking at two things. The one thing is to have a model that can be calibrated against the element level responses or the deformation patterns that you think are important, but also having a system level analysis that is emphasizing the failure mechanisms that you expect. For the element level and for one particular problem that I showed you today, the development of a semi-empirical framework for the strain rate accumulation in the cyclic mobility regime proved to be really important in our ability to capture the displacements there. At the same time, for the Balboa Boulevard case history, with all the things that we did there, the failure mechanism was much more dominating compared to the response of the elements and the fine-tuning of cyclic mobility. Both are definitely valuable to consider, especially when you're reevaluating existing infrastructure, thinking that, you know, when you're doing a new design, if you do suspect large deformations, you're going to do everything to avoid them. But when you're talking about mitigation methods for existing infrastructure, it may be really important to consider all of these aspects holistically. With that, I have no idea how much time I took, but I am done. This is all thanks to Francisco and Renmin and all their efforts. Data from Craig Davis and Los Angeles Department of Water and Power, Great Geo, and our friends in Greece, Yota and Amalia and Jacob, and of course Thalia from Fugro, who gave us access to the bar tube analysis and the experimental data from then. Gracias a todos por su atención, and that's my last Spanish. And I'm available for questions. Thank you very much.
Thank you very much, Katerina. Wonderful presentation, wonderful content, wonderful information, wonderful learning for everyone. There are some questions in the chat. Maybe the first one was mine.
Okay.
Very, I was very, I was amazed by the quality of the testing presented in the first part of the presentation. What was the frequency content in general of those cyclic tests that you presented?
The direct amplitude, usually 1 hertz.
1 hertz?
We do, yes. We haven't varied, I think so. No, it's not 1 hertz, sorry.
How much is
it? Let me see. No, we do them quite slow. We do them quite slow. I don't remember. No, it's not 1 hertz. Sorry.
That was my guess, because the curves were really, really neat. Really neat testing.
So we do those in should I stop sharing my screen?
I don't think so.
Okay. So we have a GDS device that we just got brand new up and running, and Francisco and Rachel have spent a lot of time fine-tuning that. We run the tests constant volume, so equivalent undrained, quite slow, so we don't evaluate the effects of frequencies. I think that would be a little precarious for the types of materials. Okay, so Francisco is online. It's 0.05 hertz. Sorry.
Okay. Okay.
Yeah, so it's
thank you very much.
Yeah. Sorry. Thank you, Panchito. So yeah. Now, the materials we're evaluating right now, they are Ottawa F65 sands, and we're doing some tests on either poorly and well-graded materials, New Jersey laboratory sands, going from gradations of 1 to 1.2 all the way to 6-ish. So trying to establish that a little better. Now, what else did you ask me?
That was pretty much the question about the testing.
So for the DSS
they were
test,
really nice.
So I'm gonna tell you that they're not easy. So we have developed a lot of protocols and a lot of tests, and we have thrown out a lot of data that we were not happy with. Mainly looking at, there's so many things you control, from where you measure your displacements, how you measure your displacements, slippages between the rings, tilting of the rings, how do you keep that constrained? Exactly. Effects of saturations. Some we have run saturated. Turns out if everything is not perfectly saturated, you have issues there. Some we have run dry. Most recently, we have seen effects from the stiffness of the material. So for the materials that are really, really well graded, we have problems because they're very stiff and they tend to localize. So there's a host of things to keep track of and to make it. We never throw away any data, but if you're gonna try and draw conclusions, if you're gonna try and draw conclusions, particularly for these finer aspects of the response, then it's really critical to have consistency. And now I see you posted on the 0.84. So the 0.84, so the Rinaldi receiving station is not an outcrop motion. And that was one of the problems that Renmin tackled first. So here. And the problem there was that we wanted, if you're going to do a validation analysis, you need to have the best motion available, right? Or the closest possibly. Right. And here we did not have a neighboring outcrop motion. So we said, okay, we're going to work with the Rinaldi receiving station. this actually led to a very interesting procedure. We published that in the ICEGE conference in Rome. And what we basically did is Renmin developed a double deconvolution, as we called it, procedure, such that you can basically infer from the location where you have your free field motion, let's call that free field, infer what the motion is at the bottom, and then transfer it again to the bottom of your MDA profile. It is not always important, because sometimes when you do forward predictions, you just pick a spectrum from the code, you pick some motions that honor the mechanisms that you suspect for your sites, you scale those, you will modify those, and that's it, basically. But if you want to do validation analysis and really investigate, it's really important to be able to do that. Renmin is currently performing some more research on this to try and formalize this procedure and make it broader. So stay tuned.
Definitely. Yeah. There are some more questions here. I will read them. Ramon Verdugo is the second one. Do you see? Oh no, he wrote, but he wrote it. Yeah. He asked, all the experimental evidence that was shown is from cyclic test under uniform cyclic loading.
Correct.
How do they correlate with non-uniform loads, and if you had the chance to validate them?
Okay,
that's one question.
So yeah, thank you, Ramon. This is a very good question. This is so we started investigating irregular cyclic loading back in 2013 and 14, just to see what it means for the accumulation of strains, but mostly from a more constitutive interest, less than an experimental one. Francisco right now has done a host of irregular loading tests. The protocols we follow there are that we start with a higher amplitude loading, and then we progressively reduce it, just so that we see to what extent this pattern pertains. And at the same time, what he does there is try and see what are the contributions of shear strains within each cycle. So we're interested in the strain that takes place under the very low stress regime. So basically when you are in the very narrow part of your banana loop, and then separately investigating what happens in the dilatancy part where your loops are pinching. So it seems, so the current findings that we have, they seem to be closely honoring and a little bit extending the frameworks that we see. The most important aspect, though, is that what Francisco is observing is that the one of the two parameters, like the gamma D, as we call it, the latency dependent one, will be saturating eventually, and then the gamma naught keeps accumulating throughout the loading. Overall, what we see is that eventually, and especially it came out in the irregular loading paths, it came in some other tests that we did, eventually these strains seem to be coming to an arrest. Now, the contribution of each packet, let's call them packets of amplitudes, will depend on the damage you have done before. So, which is, we're not, of course, the first ones to see that. Shamoto has seen that before. I think, who else? Yeah, I think like Wang and Shamoto and Yanis Dafalias with Rui Wang had done some DEM simulations investigating that. But I think, I mean, we are now looking at, I don't even know how many, like hundreds of tests now that we're going to be curating progressively over the next year or so that are showing that. The importance of the irregular load and dropping the amplitudes is that it's like I'm glad, like Ramon asked about this, is that this is much more representative of what happens in the field. Much more so than this, strong constant amplitude shearing that we do in the lab. So we haven't had any indications that our framework is off. until today, at least. And I don't see Francisco sending me anything, so I did not say anything wrong.
Thank you very much. Thank you very much, Katerina. There is another question from Professor Verdugo. He asked how. Actually, most of the questions are going by direct message to me, so I can
No,
do
it's
the
okay.
question.
Yeah.
How S sub U, the residual strength, was evaluated from the CPT?
The residual, we did not evaluate residual strengths. We did not do any post-triggering analysis, neither for the clays nor the sands. Perhaps this is something to consider. I mean, it was also evident in the stress strain loops you saw, we didn't see any reduction in the strength. In the PM4 silt model, we have a switch that does switch from shaking to post shaking, and it drops the strength by a value that you control. For the sands, we didn't do anything. I think Renmin, but those take a long time. We did some just like post shaking dissipation analysis, and those didn't give any larger movement than the ones we had done before. So the other thing is, like, we didn't have, other than the empirical and semi-empirical correlations by Idris and Boulanger and so on and so forth, we didn't have any other basis, because the information from the site was either like super disturbed samples just for index properties, and then the SPT and the CPT blow counts. So yeah, we didn't do a recalibration for that.
I see. Okay. Good. Mr. Juan Carlos, he asked, your presentations are always amazing, Katerina. Question. For those materials that can be identified in the boundary between sand silt, like soil behavior type, right? Like no plastic or low plasticity tailings, which is a problem that we have a lot here in Chile, right? Could you use any of these two models, PM4 sand or PM4 silt, for seismic conditions and obtain a consistent at an element level calibration for tailings? There is another question. Is any preference thinking on the industrial perspective when time is always a constraint?
That's an excellent question. Okay, so first and foremost, me personally, and I have not done specific analysis for tailings, for tailing dams from a system level, but we did with Francisco and Renmin, led by Renmin and Francisco mostly. We did a trial calibration of both models for I think it was the Fundau tailing storage.
Oh, okay.
Oh, no, it was the Cadia. The Cadia.
Brumadinho? Okay.
No, the Cadia, the NTSF. So for that, and I mean, from some of the forensic investigations, if you'd like, there were lab data available. So it was a good opportunity to just see how these do. Now, so hold that thought, parenthesis now. The philosophy of both the models, and one of the things that we have tried to promote, and by we, I now refer to Ross Boulanger and myself, is more the idea that you have to decide what you want your material to do, or what you have to decide what you think your material is doing. And then find a model that can honor that. Because at the end of the day, all the constitutive models are fictions of our understanding, right? They will do whatever we want them to do. Now, the two frameworks that we have created, the silt one and the sand one, they are similar in certain aspects, but also very dissimilar in other aspects. For the tailing materials, it has seemed to me, and without having been an expert or focused a big part of my career on these facilities specifically, they show indications of behaving sometimes like silts and sometimes like sands whenever we have seen lab tests.
Exactly.
The findings, exactly, right? So the findings from Renmin's and Francisco's work with the calibration that was published late last year in the TMW 2020 was that if you're interested in looking at the data, if you're more interested in the monotonic aspect of the response, it seemed that PM4 was more capable of honoring the data that we saw from the reports and the investigations from CADIA. If you were interested in the cyclic response and the indications that the data gave there, it seemed that PM4CN had a better framework because they were showing more pinching in the cyclic mobility regime, lower strengths in the thinner loops in the low strength regime, and so on and so forth. Sometimes here and there I will receive a question like, I have a silt material, should I use the PM4 silt model? If you have a silt material that has a very low plasticity, it will look like a sand. So you have to use a model that will make it look like a sand. It's all about, first of all, how does it behave and which framework gets you better there, right? You shouldn't go just blindly and say
the nature of the fine.
Bravo, bravo. You have to decide what you wanted to do. The frameworks are there. The frameworks are there. They have a certain set of parameters that you have to activate, right? And you have to make the decisions on. But if you're Renmin's and Francisco's investigations, they showed us, are you interested in the monotonic or are you interested in the cyclic? Moving forward, our conclusion in that paper was that if you want to do a seismic analysis, seems to us that it has to be PM4CN, the one that will give you a more representative behavior based on what we have in front of us, of course, right? So so yeah, this is the extent of at least my own experiences with this.
Very nice, very nice. Thank you. There is another question. Gonzalo, I assume this is Gonzalo Corral. He says, hi, Katerina. Thank you very much for your presentation. I have a couple of specific questions. Could you please explain the relationship between G0, shear modulus coefficient, and DR, relative density, or void ratio, as well as SU and drain shear strength into the PM for soil models?
Can you read to me the beginning of the question again?
Could you please explain the relationship between G0,
yes,
the initial shear modulus,
okay,
and DR, relative density or void ratio,
okay,
as well as SU, the undrained shear strength,
okay,
into the PM for soil models?
Okay.
I think that's, I will tell you the remaining of the questions after that.
Okay. So so the G0 is a unitless dial in the Gmax relationship, first and foremost. So that you have the small strain shear modulus, the maximum shear modulus, and that in the equation is a G0 times your P prime, your effective stress, sorry, your P atmospheric times your mean effective stress normalized by your P atmospheric, and then a power that controls how you want that to look like. Okay, so we
the Harding equation.
Bravo. So that is a 0.5 usually for sands. For clays, we have left a free index there, an NG parameter that will control that relationship subject to what the user thinks. So now the G0 inside the model, or actually as an input parameter, it's not supposed to have a direct connection with the relative density unless the user wants it to. So for example, if you have, ideally, my dream scenario is to have strength properties, cyclic strength properties, and then have shear wave velocity properties. So the shear wave velocity is going to help me constrain the low strain shear modulus, the cyclic strength properties, or in the lack of those, some semi-empirical correlations or empirical are going to help me constrain that. In the manual and in the way we do historically our calibrations, there is a relationship that we use to correlate the two, informed by Andrews-Stokey and Idrisen-Boulanger, and just connecting those. If you don't have shear wave velocity measurements, that is. The same thing happens with the SU. So as input parameters, the intention is that they are independent, right? Unless you are aware of a relationship that connects the two, right? So, and in fact, they also control very different aspects of the response. They show up, they appear, they control different loading regimes. So we're, yeah, I hope that answers. Gonzalo has my
think
number.
so.
He can.
So the second question of Gonzalo is, what can you do in the case of only having triaxial shear test, both monotonic and cyclic? Can we use them to calibrate the PM4 soil models? Thanks. That's what Gonzalo too.
Okay, so the model right now is only a plane strain one. So strictly speaking, it cannot model an axisymmetric condition, right? Call me now triaxial, okay? What we do to circumvent that, or when we have to unavoidably deal with triaxial tests, is that we run plane strain simulations, cyclic plane strain simulations. So basically a slice of your triaxial regimen, you fix it on the side, some rollers on the other side, and then you do a cyclic vertical loading as a proxy to that. And then, you know, your calibration, you know, it's not going to be spot on. It cannot be, but from our perspective, it's something close enough. Now, that said, and we also do a broad comparison of loading, the CSR versus number of cycles curves. So we will take, if we have, for example, cyclic triaxial tests, we will transform those. We will do a K0 transformation to the DSS space. Okay, and then at least also compare what we get from DSS simulations. That said, we're now working on a 3D version. So hopefully by the middle of this year, when Marie finishes, or by next year, we're going to have the ability to actually do 3D simulations and avoid all the drama from having plane strain alone. So that's what we do. Personally, when I also received triaxial data, and that was, for those of you familiar, the LEAP project that Professor Kater, Manzari, and Zegal had run. In its initial phase, when it started out in 2014, the pilot phase, they only had triaxial data. So the approach I took was I calibrated with plane strain cyclic simulations with a grain of salt. Then I calibrated against the CSR versus number of cycles curve. And then I went to the literature, and I think I found the Carraro's data or some other data and calibrated for what the literature was showing, just to have an uncertainty bound. And the predictions were fine. You know, given everything, of course, right? Taking everything into consideration, I think they were fine. Yeah.
Thank you very much. Thank you very much, Katerina. We have another question from Osmar. From Osmar, I cannot, let me see if I can. Osmar Charca.
Okay.
He has a question for you, and that's this one. How do you obtain the acceleration time for the Balboa Boulevard?
So, sorry,
it was taken
Felipe,
from the close stations?
Felipe, you cut off for a little bit. Can you read again?
Oh, okay.
Sorry.
Osmar Charca asks, how
Yeah.
do you obtain the acceleration time history for the Balboa Boulevard? Was it taken from the closest recording station?
Yes. So the closest recording station, not an outcrop, just a free field station, was the Rinaldi receiving station. Okay. So approximately, I think, two kilometers or something away. Because this was a validation study, we wanted to honor the ground motion as close as possible. What we did is we developed a double deconvolution procedure to transfer basically a nearby free field station to the bottom of our NDA profile. Okay, right. Unit D, approximately, if you remember, and that was applied as a time history at the bottom.
Good.
Because,
thank you, Katerina.
and sorry to add a little to that, since there was interest. And I don't know, like, if you want me to send you some of these papers we're talking about, and then you can disseminate, I don't know, just let me know.
Of course, we can do that.
And the other thing is, because, you know, this procedure is not, you know, just from point A to point B, transforming this motion to be compatible with the base of your NDA. That's why in one of the plots I showed you, I talked about 3 different ground motion realizations. All of them equally possible, okay? All maintained the pulse feature, which was really important, but there was some variability. For this particular site, this variability in the ground motion did not play a role.
I see. Okay. Thank you very much, Katerina. We have maybe 3 more questions.
Don't hit me.
Okay. Hector Saldaña, thank you very much, Katerina, for the presentation. I have a question regarding the calibration at element level or constitutive of constitutive models formulated in plane strain. Example given, BM for sun through cyclic triaxial test. Is it correct to perform cyclic plane strains compression simulations considering the differences between the tests? This is along the lines of what Gonzalo was presenting just minutes ago.
I don't think it is, but it's the closest possible we can do given the plane strain simulation. We track at least the plane strain simulation with a vertical cyclic loading. We track Q and P parameters to be more compatible with the invariance or with the Q's and P's that we track in triaxial tests.
Exactly.
And like I said before, yes, this is one of the issues of the model. It is plane strain. It doesn't have a cap. It is a stress ratio based. It doesn't give you plastic strains if you go along a constant K-naught line. It will not do crashing. It will not do CPT tip types of loading, which are, all of these are, you know, non-plane strain conditions, right? That's why I said before, with a grain of salt. Right? Ideally, like I said before, like my dream scenario is to have DSS simulations or hollow cylinder simulations or something like that, more to the pure shear conditions than the triaxial ones. We're working on it.
Exactly. It's a working process.
More
exactly.
or less. Yes.
Ivan Mauricio Ordóñez via YouTube. He asks, for Balboa Boulevard, in addition to the differences in soil stratigraphy or resistance, did you guys consider the presence of surface structures that may have modified the seismic input motion across the area?
No, we didn't. Two things there, or 2 things to think about. We did not, I mean, if we started to go down that road, we wouldn't even know which ones to include and which ones not. Because I mean, that's a very densely populated area. Like if you go to Google Earth and you see Balboa Boulevard to the east and the west, it's very densely populated. At the same time, all the types of structures there, and at least from my memory, those are all very it is low-rise residential structures. So we don't have like deep basements or anything like that that would modify the motion that much. The one thing that I would like to mention is that our personal expectation is that, of course, probably any buried infrastructure may change something. And we did not take anything into account from the kinematic interaction and just the existence of the pipelines in the area. One thing we are doing now with Craig, who has data for ages, is trying to reconcile now the strains we get from a 2D analysis with the strains that it would take to get those pipes to fail, because we have all information like from bedding, from thicknesses, from materials, from their age. We have information on how they failed, whether it was something that was already corroded and then the earthquake made it even worse, how it was fixed. You know, we have all that type of information. And in a more initial simplified analysis, we're trying to see if the one thing, if it was that would justify the failures. So yes,
okay,
we didn't do any
right.
substructure interaction. That
All
would
right.
have been a stretch.
Pablo Forgoso, he asks, in projects under ongoing design, how do you deal with design efforts, calibration, modeling, and evaluation of NDAs versus available time? Can you pre-estimate required time to perform a reliable NDA?
Can you read that again?
In projects under ongoing design, how do you deal with design efforts such as calibration, modeling, and evaluation of NDA versus time available? Can you pre-estimate required time to perform a reliable NDA?
Yes, I think this came up and it went through the one ear through the other. So with that, I will be honest, I'm not working in practice, and I haven't dealt with a, you know, budgetary constraints of handling something like that. What I will say, and I mean, I have been involved only from an external, you know, either like consultant or reviewer perspective. And at this point, by the time, you know, I have seen something, that means that a project manager has already put the effort forward, right? I will try and channel some of the conversations I've had with either Great Geo in Greece or Thalia and the Earthquake Engineering Group of Fugro Land, USA. I think the biggest challenge is getting up to having a group that can do these types of analysis, right? And this is an expertise that you build through the years. My impression is that more and more companies in earthquake-prone regions are increasingly building competency in running such analysis and in having staff that are either trained or on board being trained on these types of analysis. Now, the one thing I see is that no matter what, the first thing that anyone will do is just do a simplified empirical or semi-empirical procedure. Like even in Balboa, you will have seen Balboa listed as a liquefied site in the Idris and Boulanger case histories that led to the development of the triggering procedures and everything that is featured in the monograph, right? So you will do a 1D evaluation. You will see how much movement you expect, right? You will see how much budget you have from the client. You will see what other constraints are there. You will see what is the performance requirement, right? If it's a clear-cut answer that it's going to move a lot and we don't care whether it's going to be 5 or 10 or 15, then, you know, chances are you're not going to go in such advanced analysis. And I think it will also depend on the types of people you have there. I mean, most recently I saw a 1D site response analysis for a low-rise building in Oakland, where they did 1D site response analysis in FLAC with PM for silt, because they had the staff and they had the time. And, you know, the more you do it, the more you establish your pre-processing and your post-processing protocols, your plotting and everything. So unfortunately, I cannot comment from my end because I I do mostly research, so I'm gonna go to the more extreme side of things. So I don't know how to further elaborate on that. But I think one of the things to always consider is, this saying was like, just because you have a hammer doesn't mean everything is a nail, right? So, and I've heard Professor Idris say that a lot. I've heard Ross Boulanger say that a lot. Always take a step back. Go first, do some hand calculations, do the empirical procedures, just get a feel for your site. And if you require more finesse, and if you require more details in the answer, then yes, start going into more advanced analysis. I mean, when Renmin started putting these analyses together, we knew what we were getting into. Like, we knew that it was necessary, and we knew it was necessary because none of the empirical procedures were able to give these patterns, right? And he had done some preliminary calculations. And then when he did that, he did also some one-day vulnerability indices, and he did some Newmark sliding block analysis, just so that you can more holistically approximate the problem. These types of analysis. And one thing, so if you follow the Geo Institute and the GeoStrata, there was a paper that Michael Beatty and Scott Anderson wrote on NDAs and calibrations of models and everything that goes into those. If you don't have access to GeoStrata, they did an interview, just like a fun time with Jeff Dunn on the YouTube channel of the Geo Institute. And there they discuss a lot about these issues and what goes into it. And then what it takes to go over that. And it's a quite pleasant discussion. Takes about 1 hour, and it is available on YouTube. And I was listening to it the other day, and I find it very illuminating about the value and the time and the needs for such analysis.
Can we have that link later, maybe?
Absolutely.
So we can share it also?
Yeah.
There is another question here. A colleague from Turkey. Thank you very much, Katerina. I believe the material properties such as the stiffness, shear wave velocity are isotropic, which is the main assumption in geotechnical engineering. I was wondering if Katerina has considered that implementing cross-anisotropic material properties into numerical modeling would make any differences in terms of results.
Not yet. We have enough trouble from the isotropic ones. The closest thing close to anisotropy that we are considering and very relentlessly pursuing, if you'd like, are the effects of static shear stress ratio. In a way, you could consider that as a form of anisotropy. We are still collecting data on that, but we haven't evaluated anything else beyond that. That is a conversation for after Ross retires. So for now, no, we haven't.
Yeah, anisotropy is always an issue, right?
Yeah, I mean, and that's what I said. Like we have only seen an anisotropy, from a pre-shearing perspective. In a triaxial test, I mean, it's going to be a true anisotropy. In a DSS test, I don't think that I have seen it explicitly ever called anisotropy.
Yeah.
So
yeah,
so that's
always an issue.
Yeah.
Yeah. Pancho Mire, he has a comment here, and he says we are working in a database that includes tests on soils with different gradations, including tests with a sloping ground and irregular cyclic loading. Bravo. Stay tuned for future updates.
Bravo, Panchito. Yes.
Yes, it would be great to have that information too.
Yes, so all of that I can let you know. Our plan is to curate everything in Design Safe. which is free access from everyone, really. So I think, you know, and needless to say that Francisco and Rachel have done amazing, very good job in curating and documenting and evaluating all the tests. So yeah.
That's very important.
Yeah,
That's,
and in the chat, I have now posted,
very
and I have
useful.
I have put the YouTube link to the interview I talked about, and the paper. If you have access to the Geostrata magazine, it's not a research paper, but I think, you know, both these, because both Scott and Mike do high-end consulting, and for all types of structures, they really share some of their, you know, perspectives, and I found it very well balanced, to be honest, like very realistic.
Great. Thank you very much for the information.
You're welcome.
Camilo Morales, he says, thanks for the presentation. Is UC Davis Research Group conducting research in soil dynamics with the material point method? How are you dealing with large deformation results in dynamic FE or FD analysis? Is it an issue?
We don't have an expertise in MPM. We have used it more out of curiosity and just more from an evaluative perspective about whether this would be something worth pursuing as a research or a utility. Basically, we do have expertise, mostly the groups of Alejandro Martinez and Jason DeYoung on the discrete element method. So they're doing like DEM simulations, not so much for earthquake problems. One of Alejandro's students is investigating the effects of cyclic loading and fabric. But, you know, all things realistic, DEM, you have to consider the size of particles that you can feature there, and the extent to which this can give you a usable answer. And also, you have to find a way to connect that to the field. So the answer to how do we deal with large deformation problems? I've dealt with large deformation problems in FLAC. It hasn't given me the large MPM type of answers. It has given me more tendencies. So in the simulations we did, 2014 published in 2015 in the ICEGE conference in New Zealand, we did the simulations of a delayed flow failure in the centrifuge. And that's a flow failure that really took off, like it pancaked, basically. FLAC did not give me that, but FLAC gave me the formation of a water film. It gave me the progressive acceleration of the mass. It gave me large deformations. So from that point and on, and in terms of decision-making, I said, yes, it's gonna move a lot. It cannot give me the run out. It cannot give me run out of like the Oso landslide or of any like experiments that have run out or like tailing storage facilities that have run out. But depending on how fine of an answer you want, like if it's gonna move 200 meters, doesn't matter if it's 250, you know, depends. If I don't care, FLAC can give me that very comfortably. If I care about refined answers, then at some point, yes, we have to move to other platforms and other numerical capabilities. But we don't do that right now.
Nice. Very nice. Very nice. I think we have two final questions, and that would be it. Alfonso Serna, nuestro amigo Alfonso Serna. Were the simulations done fully undrained? What are your thoughts on the flow conditions in the simulations?
They were fully coupled effective stress analysis, neither total stress undrained nor drained. I assume Alfonso is referring to the Balboa Boulevard or the bar tube. Either, both were coupled effective stress analysis.
I see.
In terms of the regime of flow, I'm not sure what the question is there. I mean, it's not a UPU formulation being able to track the migration of water throughout the deposit. And also it's fully saturated. So we're not evaluating, or at least for the zones that we assume fully saturated, they're fully saturated. And then we don't consider any partial saturated zones.
Okay.
And frankly, I have not, at least me, done any usage of UPU formulation.
Great.
I have seen it. Boris at UC Davis does that a lot. It's fully verified and validated. From my perspective, it's also, okay, let's assume you did it. How do you know it's right? How do you know that this is what happens in the field? So I'm trying to keep my eyes on what is realistic and feasible, I guess.
I see. Good. Thank you. Thank you, Kate. Felipe Cuncar, regarding the results of the first part, all the parameters of the numerical model were calibrated before the centrifuge test, or there were adjustments after having the results of the physical model?
I assume this refers back to the BART tube analysis. So we had a baseline calibration. So historically speaking, just so that we have an idea, there were first some analysis of the Fugro BART tube by Fugro. At the time, they were stationed located in Oakland. They did the first analysis with just, some field information they had. Those analysis ended up showing that the BART tube is not going to move much. But because that was a very high consequence decision, they didn't take any risks. And then they went to Davis and they did the tests, at the time led by Bruce Cutter and Ray Chu, who is now a professor in Taiwan, in Taichung. So they did the tests and then they got their data and then they revisited their analysis and then they did more refined calibrations with Nevada sand data from Annie Kemmer at the time and Michael Reamer, and then Monterey sand as well. So they did the calibrations. At the time, PM4 sand was not available. The very first analysis they had done were performed with UBC sand. I don't know which version. I think it was the 904, not the 904AR, but no big deal there because that version came out a little later following like the Success Dam calibrations. So they revisited those with UBC sand and they calibrated the model after the test, and they got the very first predictions of the displacements. Of course, they did some sensitivity analysis, but the overall outcome was no matter what uncertainty you got into there, the displacements never really took off. So there was no, fear that the tube would just like float up to the surface of the water. So after that, they said it's safe-ish. They did some mitigations. They saved millions of dollars to Caltrans because mitigating is very different from reconstructing from scratch. The calibrations we did when we came in, yes, we started from the initial baseline we had, of course, but then we switched completely the models, right? We implemented PM4 sand. We did the triggering calibration then. Of course, we had done first, I did not show it, but we did do an analysis without looking at all to the post-triggering deformations, just like baseline triggering, some shear wave velocities, some calibrations there, and that's it, right? If the implied question is to what extent does that affect the quality of the predictions, I don't think it does, because we do things blindly. In a way, just kind of like we're not doing any fine tunings by looking at the results. First, we do like one point A to point B prediction, see what we get, and then we revisit. But we never, and I will say that quite confidently, we never do this thing of fine tuning just anything to get the right answer. You really want to just fine tune the things that are going to be found to be meaningful and things that you can support. Things, I mean, I always, the joke that I say is like, would you write that in a paragraph? Or how would you write that in a paragraph? Or how would you support this in a review board as a choice? right? So this is historically how we have done stuff in terms of the calibrations.
Thank you very much. Thank you very much. That we finished the round of questions, Professor Ziotopoulou.
Okay.
So, Kates, yeah, right. So it's been wonderful. This has been a wonderful presentation, a wonderful talk. We went a little bit over the time. I think we apologize. We had many questions.
Who froze?
And thank you very much to everyone for coming here.
So I thank you a lot. I wish I would see all of you in person.
Yeah, next time it's gonna be in person.
So I'm not going anywhere. We still have a pandemic. I'm in my computer all the time. If you have questions, or if you need any papers, just shoot me an email or ask Felipe, or I can give a bunch of stuff to Felipe and then he can if you ask me hard questions, I'm going to refer to Renmin and Pancho. So because they have been doing all of the work, really. So yeah, I'm happy to share all we have.
Thank you very much, Professor. Thank you very much, Professor Katerina. And thank you very much. It's over. I will stay here with the academic team of the seminar. We will let everyone go. And thank you very much. And we'll see you very soon for the next geotechnical seminar of University of Chile. Thank you very much. A virtual clap for Katerina for this wonderful talk, wonderful presentation.
I'm putting the heart. Thank you all.
we learned too much today about especially about all the things that have been that you have been doing lately, especially with the paper on the boulevard.
These two works that I showed you, honestly, these two works that I showed you, they are my favorite ones.
It was recently released, maybe a month ago.
Oh yeah, those are very fresh. But the work that you saw from Renmin and all the newer things he has been doing, and also all the data and the testing and the frameworks that Francisco has been working on, both of these, I think, and I don't talk very frequently like that about our work. I think those are going to be really good. I am really excited. So I will keep you in the loop for sure.
Thank you very much, Professor Katerina. Thank you very much to everyone. And we cut the broadcast. We stay here with Katerina.
Thank you.
And the rest of the academic team. Thank you very much to everyone for coming, and see you in the next seminar.
Thank you so much all.
Bye-bye.